Welcome to the Deep Dive. Today, we're going straight to the heart of, well, a pretty huge global challenge, the future of our coastlines and the stark reality of sea level rise.
Yeah, it's a big one. And we've got two key sources guiding us today.
Exactly. First, there's a really compelling report from The Guardian, which unpacks the findings of a major new scientific study.
And we also have the study itself, the peer-reviewed paper published in Communications, Earth and Environment.
So our mission in this deep dive, really, is to pull out the most critical insights from these for you.
Right. We want to cut through some of the complex science and get to the core question. How much sea level rise should we actually be preparing for?
And what does it mean even if we, manage to hit our climate targets?
Yeah, that's a crucial part of it.
Okay, let's dive right in with something that honestly kind of changes the whole perspective.
What's that?
This research shows that ice loss from Greenland and Antarctica has actually quadrupled since the 1990s. Quadrupled.
Wow. That's a massive acceleration.
It really is.
Yeah.
So it's not just like slow melting anymore. The main driver of sea level rise has shifted and intensified towards these huge ice sheets.
Okay, so let's unpack what the study predicts. It sounds pretty dire.
It does. The study basically says that even if we somehow manage to keep global temperature rise below that 1.5 degrees Celsius target everyone talks about,
Sea levels are still going to rise relentlessly.
yeah, making coastal defenses incredibly difficult and potentially leading to what the scientists call catastrophic inland migration.
And the warming we already have, right? Around 1.2 degrees Celsius. That's already a problem in itself, according to the study.
It is. But this next bit, this really made me stop and think about that 1.5 target. The world isn't really on track for 1.5, is it?
No, not currently. The trajectory is pointing towards something more like 2.5 to 2.9 degrees Celsius of warming.
And at that level.
Well, that's where the risk gets incredibly high. The sources suggest it could trigger the irreversible collapse of the Greenland and the West Antarctic ice sheets.
Which would mean,
If that happens, we could eventually, over time, be looking at around 12 meters of sea level rise.
12 meters. That's hard to comprehend.
It's a landscape-altering amount, a total reshaping of coastlines globally.
And to put that 12 meters in context, the study mentions that right now, about 230 million people live within just 1 meter of the current sea level.
And a billion people within 10 meters.
A billion. So this 12-meter rise, are we talking something sudden or over centuries? And what would be the first signs?
Good question. The 12-meter figure, that's the long-term potential, unfolding probably over centuries, maybe millennia, after the ice sheets really become destabilized.
Okay.
But the start of that destabilization, the trigger, that could happen much sooner. The key signs are exactly what we're seeing now, accelerating rates of ice loss.
And even much smaller rises have huge economic costs, right?
Oh, absolutely. The study points out that even just 20 centimeters of rise by 2050, which is well within projections, could cause over $1 trillion in flood damage annually for the big coastal cities.
$1 trillion a year. That's not just financial. It's societal disruption on a massive scale.
Exactly. Cascading failures, logistical nightmares of moving people, infrastructure. It's huge.
So it sounds incredibly grim, but is there any sense that the scale of this is still, somewhat in our hands?
Yes, definitely. That's a critical point that scientists make. Every single fraction of a degree of warming we can avoid still matters enormously.
Oh, so.
Because even if we can't stop sea level rise completely, slowing it down buys us time. Crucial time to prepare, to adapt. It reduces the scale of the suffering, the displacement.
So mitigation, cutting emissions, is still absolutely vital.
Absolutely. It makes a real difference to the rate of change, which is key for adaptation.
Okay. This really makes you question those benchmarks, like 1.5 degrees.
Yeah.
Which brings us neatly to that point.
The 1.5 degree illusion, as you might call it.
Is 1.5 degrees C really the safe limit we've often assumed it is, especially for these massive ice sheets?
Well, this study argues pretty forcefully that, no, it's not a safe limit for the long-term stability of the ice sheets.
So important for other climate impacts, maybe, but not for preventing major sea level rise from ice.
That seems to be the core argument. For the ice sheets, 1.5 degrees C is likely already too high to prevent significant long-term rise.
Okay, so if 1.5 isn't safe for the ice sheets, what is? Did the study suggest a different number?
They hypothesize, based on the evidence, that a truly safe limit, one that allows adaptation rather than forcing catastrophic migration, is probably closer to just 1 degree Celsius of warming. maybe even lower.
1 degree. That's much lower than current targets.
It is, and they link that to a rate of sea level rise around 1 centimeter per year.
Ah, that specific rate.
Mm.
Professor Jonathan Bamber's quoted talking about that, isn't he? Saying adapting beyond 1 centimeter per year gets extremely challenging.
Right, and could lead to massive land migration on scales that we've never witnessed. It paints a very stark picture.
And Professor Chris Stokes, the lead author,
Yeah.
they seem quite concerned.
He expressed real concern that what used to be seen as worst-case scenarios are actually starting to happen now.
And that the current acceleration, even at 1.2 degrees, could become unmanageable relatively soon.
Yes, within the lifetime of young people today, if that acceleration continues, it's a sobering warning.
There's also that technical point about how 1.5 is defined, right? It's not just 1 year hitting the mark like 2024 apparently did.
Exactly. It's officially defined as a 20-year average.
So we could bob above 1.5 temporarily without officially breaching the target.
Yes, and the concern is that this averaging could mask the ongoing damage being done to the ice sheets. It might delay recognizing the severity and slow down the response needed.
It definitely makes you think about how effective these targets are in driving the necessary action. Maybe looking back at Earth's history can give us more context.
Absolutely. Past warm periods are like natural experiments. The researchers looked at times like the last interglacial, about 125,000 years ago.
And temperatures then were similar to now or slightly warmer.
Estimates are around 0.5 to 1.5 degrees warmer than pre-industrial times. So very relevant to our potential future.
And sea levels back then.
They were significantly higher, somewhere between 6 and 9 meters higher than today.
Wow. 6 to 9 meters higher, with only slightly more warming than we have now. Where did all that water come from?
The evidence points to contributions from both Greenland and Antarctica.
And it wasn't just the total amount of rise, but the speed, right? You mentioned meltwater pulses.
Yes, meltwater pulse 1A during the last glaciation. Sea levels rose at an incredible rate, maybe 3.5 to 4 meters per century.
That's 10 times faster than the current rate.
10 times faster, driven by these powerful feedback loops within the ice system.
Right. Feedback loops. Can you break those down a bit? What makes the ice melt speed up so dramatically?
Sure. One key one is the surface elevation feedback. As the ice surface melts and lowers, it reaches warmer air at lower altitudes, which makes it melt even faster. It's a self-reinforcing cycle.
Okay, that makes sense.
Then there's marine ice sheet instability, or NSI. This happens when an ice sheet rests on bedrock that slopes downward away from the coast, below sea level.
Right.
If warm water melts the edge, the grounding line where the ice starts to float can retreat rapidly downhill, potentially destabilizing a huge area of ice behind it, like dominoes falling.
And there was another one, MICI.
Yes, marine ice cliff instability. If a floating ice shelf collapses, it can expose very tall, unstable ice cliffs at the edge of the grounded ice sheet. These cliffs can then just crumble rapidly into the ocean.
So these feedbacks mean a small initial warming can trigger a much larger, faster, and potentially unstoppable response.
Exactly. They can become self-sustaining, leading to rapid and on human timescales, potentially irreversible ice loss.
Irreversible. That's the really worrying part. Okay, so turning from the past to the present, what are the latest observations telling us about how the ice sheets are behaving right now?
Well, the satellite data since the 90s is pretty clear and, frankly, concerning. As we said, mass loss from Greenland and West Antarctica has sped up dramatically.
East Antarctica, too. Or is that more stable?
It's been closer to balance overall, but there are large uncertainties, and some worrying signs of increasing loss are emerging there too, particularly in areas like Wilkes Land.
And the actual amount contributed to sea level rise.
Between 1992 and 2020, the ice sheets added about 21 millimeters to global sea level, but the key thing is the rate it's been accelerating.
And didn't you say the recent losses are tracking the high end, or even exceeding the IPCC projections?
That's right. The losses from 2007 to 2017 were already at the upper range of the projections made back in the IPCC's fifth assessment report. And data since then suggests it might be even higher now.
Let's talk Greenland first. What's the main culprit there?
Surface melting is a huge factor, and it's being supercharged by Arctic amplification. The Arctic is warming nearly 4 times faster than the global average, which really hits Greenland hard.
And this recent melting is unusual.
Very unusual. Looking back over the last 180 years or so, the recent mass loss is unprecedented and seems largely driven by external human-caused warming, not just natural cycles.
Okay, and Antarctica, especially West Antarctica, Thwaites Glacier, Pine Island.
Yeah, the Amundsen Sea sector in West Antarctica is a major hotspot. The primary driver there seems to be warmer ocean water, that circumpolar deep water, getting underneath the floating edges of the glaciers and melting them from below right at the grounding line.
And that's the trigger for that marine ice sheet instability you mentioned.
It could well be. It's certainly consistent with the early stages of NSI. And as I said, even parts of East Antarctica, like Wilkes Land, are showing similar patterns linked to ocean warming.
Is any of this just natural variability?
Natural variability always plays a role, of course, but the weight of evidence now strongly points towards anthropogenic, human-caused forcing as the dominant driver of the recent accelerated ice loss from both poles.
Okay. So given all that the past, the present accelerating melting, what do the projections say about the future? Even if we really knuckle down on emissions.
Well, even the low-emission scenarios, the ones aiming for 1.5 degrees, show continued sea level rise from the ice sheets through this century and way beyond. There's a lot of inertia.
Inertia, meaning the changes are already baked in to some extent.
Exactly. Some studies are suggesting that the 1.2 degrees of warming we already have might have committed us to several meters of sea level rise over the long term, hundreds or thousands of years.
Like pushing a boulder downhill, even if you stop pushing, it keeps rolling.
That's a good analogy. We might have already set processes in motion, particularly in parts of West Antarctica, that will continue regardless of near-term emission cuts. It's called committed sea level rise.
And temporarily going over 1.5 degrees makes it even worse.
Significantly worse in the long run, yes. Even just maintaining today's level of climate forcing around the 2020 level without adding more warming could still lead to substantial future rise because the ice sheets haven't fully adjusted yet.
You mentioned committed tipping. What's that?
It's the idea that we might have already passed the threshold for irreversible retreat in some areas, like parts of West Antarctica. That alone could lock in something like 2.7 to 3.5 meters of sea level rise over millennia.
And even if we could magically pull all the CO2 out and cool the planet back down.
The ice sheets would take hundreds, probably thousands of years to regrow. So land lost to the sea in the coming centuries is effectively lost for a very, very long time on human timescales.
Okay. This really underlines the long-term consequences. So let's synthesize this. What's the final verdict on the 1.5 degree target, specifically regarding sea level rise from ice sheets?
Pulling together the evidence from past climates, current observations, and the models, the researchers make a very strong case. Plus 1.5 degrees Celsius is simply too high to prevent major, significant, and potentially catastrophic sea level rise from the polar ice sheets.
So what should the target be, according to them?
They hypothesize, based on all this evidence, that a safe limit, safe for the ice sheets, that is probably lies at or below plus 1.0 degrees Celsius above pre-industrial.
1 degree. Back to where we were roughly in the 1980s.
Essentially, yes. A time when the ice sheets were much closer to being in balance. This thinking also aligns with earlier calls for a safer CO2 concentration limit, around 350 parts per million.
So they're advocating for a much stricter target based on a precautionary approach.
Precisely. Given the potential for irreversible collapse and the huge uncertainties around these tipping points, they argue we need to be much more cautious and aim significantly lower.
Okay, let's try and recap the absolute key takeaways here. First, even hitting current climate targets like 1.5 degrees won't stop significant sea level rise. It's already locked in to some extent.
Correct. Second, the stability of the big ice sheets seems much more sensitive, the situation more urgent than maybe the public discourse reflects.
Third, looking at the past and the present behavior of the ice sheets points very strongly towards needing much, much lower warming targets, like 1 degree or less, if we want to avoid really major sea level rise down the line. For me, the real aha moment is that realization that 1.5 degrees, which we often hear framed as the threshold to avoid disaster, is probably already too high if your main concern is preventing catastrophic long-term sea level rise from ice melt.
Yeah, it reframes that target significantly. And for you, the listener, taking this on board gives you a deeper and maybe more sobering perspective on the climate crisis than you get from just the headlines.
It really highlights the incredibly long-term nature of these consequences and just the immense scale of the challenge that stretches out for centuries no matter what we do now.
It's a multi-generational issue, truly.
So here's a final thought to leave you with, something to chew on. We know now that even if hypothetically all human-caused warming stopped dead today, sea levels would still keep rising for centuries because of the inertia in the oceans and ice sheets.
Right. The system is still adjusting to the warming we've already caused.
So, given that inevitability, what kind of truly bold, maybe even radical solutions do we need? Not just thinking about cutting future emissions, but about actively adapting to the significant sea level rise that's already baked in.
Hmm.
Does it force us to think beyond traditional defenses and consider completely different ways of living with dynamic, changing coastlines over the next few hundred years? It certainly makes you wonder if our current adaptation plans are ambitious enough for the long